Last chapter, we're going to continue with bonding. Up to this point, we've looked at, of course, started off with ionic bonding, simplest. Then we went into covalent bonding, but we looked at actually the historical order of how the theories about covalent bonding developed. Is how we've taken it. And we've looked at the valence bond theory and a couple of models that were derived from that, like the localized electron model and the VSEPR, which gives us an ability to draw structures. But there are limitations, as with most theories. And this illustrates one of those major limitations to the valence bond theory. And that is when we try to explain some molecules, the Lewis structure for methane, for instance. If we use our standard procedure, then this has 4 electrons, and that has 1 times 4 is 4 is 8 electrons. Okay. So we should draw like this, 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 and this. 1, 2, 3, 4. So we've used up all of our electrons. And we should expect that to be a tetrahedron. Okay? And it is. And the bond angles are 109.5 degrees. So as far as that goes, the theory works. The problem is the valence bond theory says that bonds that are used to form these right here, these single bonds, are derived from the individual atomic orbitals that overlap for these guys. Okay. Now with carbon, right? Carbon is, let's see, 6. Yeah, 6. 1s2, 2s2, 2p2. Okay. That's the atomic orbital structure. We're supposed to be able to use these valence orbitals to form that molecule. Right? If we do, then of course this is the core, so it doesn't count. So if we have a carbon with a 2s orbital, it's going to be spherical, right? But then the 2p orbitals go like this, and then into the background, like that. All right? So if you form, if you take the s orbitals and you form a bond with the hydrogens, and then you take the p orbitals and form a bond with the other 2 hydrogens, you don't have equal bonds because the s and s overlap for these 2 hydrogens is one orientation, and the s and p overlap for these 2 would be a different orientation. So the bond angles and bond strength should not be the same, but they are. I mean, the physical evidence and examination of this molecule says that the tetrahedron is the right structure. So we predict the right structure, but we can't explain it because the localized electron model says the bonds are formed from overlap of atomic orbitals. So how do we get around this problem? Well, we tweak the theory. And we use a word. Hybridization. We hybridize the atomic orbitals of carbon. And now we have 3 equivalent orbitals that are formed from 1s orbital and 3p orbitals. Right? So we have 4 of these available to us. 4 sp3 orbitals with equivalent structure and direction. Now, if we overlap a hydrogen with each one of these, they're equivalent orbitals, equivalent bonds. Okay, would expect, like I said, S2P2 to be the source of our bonding orbitals, but they don't work because they're oriented differently. So, because the experimental evidence says that we have to have equivalent orbitals, we've got to adjust our theory to take that into account. So we hybridize the orbitals, and this method modification was proposed by Linus Pauling in 1931. And he says it works for simple molecules. So that's where we started. We just hybridized the orbitals. Okay. And in the process, the modifications to the quantum mechanics of the orbitals had to be introduced. Because quantum mechanics says that you have to have an S and three P's separate. So they had to modify the equations for those, the wave equations originally proposed by Schrodinger. Schrodinger. Okay, so Sp3 hybridization gives you a tetrahedral arrangement. But we don't stop there. Right? It depends on what we need to produce the right results. So hybridization, this is just the stepping off point. We're gonna advance, and wherever necessary, we're gonna hybridize. What we see is, and this comes out of the quantum mechanical modifications, we find that these Sp3 hybridized orbitals are somewhere, energy-wise, are somewhere in between two P's and two S's. Now, we know that the principal quantum number is roughly an estimate of the energy at that level. But the S's are lower energy than the P's. That's why they fill first when we're adding electrons. But when we hybridize them, they have to be equivalent energies. Otherwise, the bonding won't give you the structure you want. So they're somewhere in between the P's and the S's. Okay, and this is what the computer model says they look like. They have a big bulb on one side and a tiny one on the other. So we form a bond here, 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 and here, and we have 4 hydrogens taken care of. Okay. Now, we don't have to hybridize the hydrogen. We can overlap that orbital with one of these, and everything's hunky-dory. So how would we describe the this hybridization if we had to use it for a different molecule, like ammonia? Ammonia's only got 3 hydrogens that it needs to bond. I guess we're going to get to it in a minute. So we have to describe the bond, describe the structure, the Lewis structure first. Then we have to determine the arrangement with VSEPR, which still works. I mean, that part of it works. This is an operational model, and it doesn't actually explain what's going on underneath. And then we have to use that to determine the hybridization that's required. Now, hybridization doesn't necessarily, it's not necessarily restricted to what in the world? It's like a drunk fly. Hybridization isn't necessarily restricted to the orbitals that are going to be involved in bonding. It can also involve lone pairs, right? Orbitals that are occupied by non-bonding electrons. So in this case, where we have ammonia, we draw the structure, we find that we have a tetrahedral electronic structure, right? with 4 electrons, 2, 4, 6 electrons, or 3 pairs involved in bonding in one lone pair. And that minimizes repulsion. Now, everything we understand that up to this point. As it turns out, Sp3 hybridization is the best way to go because we're saying that the electronic structure is tetrahedral. And the tetrahedral structure for the electrons automatically says Sp3 because we need 4 equivalent orbitals, 1 here, 3 there, to be occupied by both bonding and non-bonding electrons. Okay. Yeah, I just said that. Now, the bond angles are like anything else. We predict that with tetrahedron there'll be 109.5. But we have to modify that and match the evidence. And the evidence says the bond angles are less than 109.5, like 108 or 108.5 or something like that. Smaller because this lone pair up here, even though it occupies an equivalent hybrid orbital, tends to balloon out. It's got no other atom on the other side restricting it. So it just kind of bulges out and puts pressure on these 3 hydrogens to move further away. Okay, how about C2h4 Ethylene? Right? Did we do this one before? Ethylene. So we have 2 carbons and we have 4 hydrogens. So we have 8, 9, 10, 11, 12 electrons. We have 2, 4, 6, 8, 10. So we got 2 electrons left. We can put them here, but now we have to make an octet. So we just move these 2 over here and make a double bond. Okay, so that's your Lewis structure for ethylene. Now, around each carbon, we could have different structure. But since these are equivalent carbons, we've got 1, 2, 3 around that one, 1, 2, 3 around this one. So that means this one is trigonal planar. And this one is trigonal planar. Okay, they're both the same. Which means they should look like this. With this equal trigonal shape here. Okay, now we have to decide, well, the bond angles we're expecting, right? 120 degrees. 120, 120, 120, makes 360. So the bond angle should be 120. And how do we get that? Well, in order to do that, we have a different hybridization required. With only 3 orbitals required, and 3 orbitals required, we get an Sp2 hybridization. It gives us 3 equivalent orbitals. That gives us the trigonal planar structure. But you may be asking yourself, we got 2 bonds here. You know, this only accounts for 3, 1, 2, 3. So what happens to that other bond? Okay, I think I got pictures to show you there. Trigonal planar, 120 degrees. There's our structure. Okay, so Sp3 hybridization will work because that gives you 4 equivalent orbitals, and then you'd have 1 left over just hanging out there. So we do Sp2 hybridization to give us the trigonal structure, and then the double bond comes from an unused p orbital. Say this is p x and y used in that one. This is the z orbital that's not hybridized. Okay, so it would look like this if you had a single bond over here with this carbon, like that, you would have an unused p orbital there. And then this carbon would also have an unused p orbital, right? So the double bond comes from overlap here. Those p orbitals overlap and give you the double bond. Now, the on-axis, let's see, we're probably going to describe that. I might as well do it now. The single bond, whenever you have a single bond between two atoms, they're on axis between the atoms is the bond. Those are always called sigma orbitals with a small Greek letter S, sigma. These off-axis types are called pi bonds. Okay, so sigmas are always on axis, pi's are always off axis, but you can only have a pi after you have a sigma. The sigma is what it does first, then if necessary, makes a pi. So you can have, if you've got enough p orbitals, say we only created an Sp hybridization, then you have two unused p orbitals, one this way and maybe one this way, that could overlap. So that's how you get a triple bond. You get two pi bonds and one sigma. Okay, we're probably going to talk about that a little more with the slides anyway. Yeah, in fact, there it is. So the electron pair that's shared on axis is the sigma. You can only have one of those because there's only one axis between atoms. But the pi bonds can be off axis in two planes. So you can have two pi bonds available. Okay. When you've got Sp2 hybridization, then you're only going to have one available unused p orbital. So you can only have that one pi bond. When you have, well, okay, I'm getting ahead of myself. We have the Sp2 hybridization here, which is somewhere in between the P and S. But this unused is still at the same energy level as the original P. It doesn't change. So here's what it would look like, an artist's rendition. So you have trigonal planar because these are all equivalent, pointed to the apices of an isosceles triangle. And then you have the unused p orbital here available for pi bonding. And this is what an artist thinks they look like. Okay. There's another discussion. It doesn't add much to the discussion, except it gives you a little better perspective than my drawing, overlapping these. Now, this is just one double bond. They show it overlapping these both bulges, but those are probability distributions. And this overlap and this overlap doesn't mean two bonds. It only means one bond. Okay. What's the shape of the carbon dioxide molecule? All right. We've done that one before. Carbon dioxide. Like that. So we've got linear, right? A linear molecule. So how do we account for that? Well, we only need a linear only needs two hybridized orbitals at opposite ends, actually, 180 degrees. So we only need to hybridize an S and a P to give us two. You got one S and one P gives you two sp orbitals. So we've got one bonding with this oxygen, one bonding with that oxygen. That gives you the linear structure. Now we've got two P's that are unused, right? If this is a PX that was involved in that hybridization, now you've got a PY and a PZ unused on that carbon atom. Okay? How about the oxygens? Well, the electronic structure of the oxygen would be 1, 2, 3, or trigonal planar, which means Sp2 for the oxygen and Sp2 for that oxygen. So that means each of these oxygens has one unused P. Okay? So this unused P overlaps with that unused P, and this unused P overlaps with that unused P to give you the pi bond on this side and the pi bond on that side. So the sigmas are formed from these, one of these. Two of these here, like there are three Sp2 hybridized orbitals. Two of them are occupied by lone pairs, and one of them is used in a sigma bond. So you've got a sigma here, and then the pi is formed from these P overlaps with one of these two Sp orbitals. Okay. Let's see if the slide explains it any better. Let's see. Well, it sort of gives you an energy idea. Here are your two unused P orbitals for carbon. And here are the two hybridized orbitals. One used on that side, one used on that side. And then these two are used with the pi bond for one oxygen and the other oxygen. There you go. That's what an Sp hybridized orbital looks like. Okay. So there's your pi bond overlap here. And then this one occurs in, let's see, it should be, yeah, here we go. This one with that one, this one with that one. Actually, the best way to represent that would be, this would turn a little bit. So that one would be in line with that one. Okay. I guess this is showing the sigma overlap first here. The Sp2 hybridized oxygen overlaps with the Sp on the carbon. These are just the sigma bonds. This is a better representation because this one is turned like that to overlap with the unused P that's sticking out this way. This one is like that, so it can overlap with the unused P that's going this direction. Okay. How about the N2, the dinitrogen molecule? How do we explain that one? Okay. It's a linear molecule, so it's got to have Sp hybridization. Okay. So Sp hybridization would be sufficient to bond this nitrogen with that nitrogen. And then you have two unused P orbitals on each nitrogen to overlap and give you a pi orbital here and a pi orbital there. Excuse me, pi bond, not orbital. A sigma bond versus a pi bond. Okay, let's see. We're going to have any more, or can I draw a chart up here to kind of pull everything together? That's another three-dimensional view. That's before we get into that. Let's say we have our VSEPR shape and the hybridization that accompanies that. Okay, so if we have a linear structure, we should expect to have Sp hybridization because we only need 2 equivalent bonds. If we have trigonal planar, we should have Sp2 hybridization to give us 3 equivalent bonds. And if we have tetrahedral, this is electronic shape. Tetrahedral, we have Sp3 hybridization. Okay? That doesn't cover everything we've looked at in VSEPR, does it? What about trigonal bipyramid? Bipyramid. That needs 5 orbitals, right? We've used up all our S's and all our P's. So where do we go from there? D, all right. Use up, grab a D, hybridize a D in there. So with a D, Sp3, it's 3, 4, 5. There we go, we got 5. Now, don't ask me why we put the D first. I would expect to put the D back here, but maybe it just sounds better. DSP3. And then the other one we've got is octahedral. So we know the pattern. We're going to need 2 Ds. There we go. Now we got all the bases covered that we're interested in so far. I mean, you can go beyond that, but not in this course. Okay, so trigonal bipyramid, right? You have these different angles. And this is how we get them. Let's see. We're expecting these chlorines, which do not hybridize because they only need 1 overlap, 1 bond. But the phosphorus needs 1, 2, 3, 4, 5 orbitals. It's not going to show us that. It didn't tell us the hybridization. Okay, maybe it's coming. And here's your octahedral. There we go. There we go. Oh, we skipped the DSP. Or did I bump it and go past it? Yeah, I did. Sorry. There it is. DSP3 hybridized orbitals. Now this only works when the atom has access to d orbitals. So with phosphorus, yeah, phosphorus is in the 3rd period. It has access to 3 Ds. So that works. You can't hybridize up here with d orbitals because the 2nd period doesn't have access to them. 3rd period does have access and beyond. Okay.
Do you mind if I go home and watch that and already put it on there?
No, that's no problem. If you're,
I hope that the family plans so good.
you got to get medicated, right?
I hope so. I say we have some at the house. I hope so somewhere.
Yeah.
Have a good one.
Okay. You got a copy of everything. Yeah. Good deal. We'll see you next week. Okay. Okay. So combination of 2 D1s, let's say, given octahedral arrangement of 6 equivalent hybrid orbitals. Okay. How do we know the hybridization is not Sp3? Right. Sp3 hybridization would give us a tetrahedral shape. And we know from experimental data that the shape of the molecule, back up, the shape of this molecule is square planar, right? Each one of these is in a square. It's not in a tetrahedron. Oops, wrong way. There we go. So there's our physical evidence that says it can't be Sp3 hybridized. It has to be D2sp3. So we have to include the lone pairs in this hybridization scheme. See how complicated it can get when your model fails to answer the question and you start modifying it. Then very often you create more problems than you solve. So we've solved some problems now, but eventually it's going to create problems that can't be overcome. Okay, Xenon Tetrafluoride is another example of D2sp3. And when we say, I just remind you, we're talking about the electronic structure because the lone pairs have to be included, at least for now. I can think of some examples, particularly with organic chemistry, where the lone pairs are left out of the mix. But for now, this is where we're at. Okay, how about HCN? All right, we know that's a linear molecule, correct? So linear means it has to be sp hybridized for the carbon. How about the nitrogen? How is it hybridized? Let's draw it. HCN. The N has a lone pair out here. So if it's going to be linear, then nitrogen also has to be sp hybridized. And the carbon is sp hybridized to give us equivalent 2 sp orbitals. And this one, let me see now, that might. Do we need sp hybridization? We should, because it's linear. Yeah, okay. I started to doubt myself for a moment. And then the pi bonds are formed from unused. So we've got 2 unused P's and 2 unused P's that form the 2 pi bonds. And this lone pair occupies the other sp orbital. That's one is bonding and one is lone pair. There we go. So we've got 1 sigma bond over here. That's it. 1 sigma bond over here. And 2 pi bonds. Okay. I'm going to have to erase this to make room. Well, maybe I didn't have to. I could draw on the board. Sometimes I forget where I am. Okay, bond angle and hybridization for these molecules. Well, we already did these, right? This one is tetrahedral, so it's going to be Sp3 hybridized with 109.5 degree bond angle expected. This one is a linear structure, so it's Sp hybridized with 180 degrees. SO2. That's 3 times 6 is 18 electrons. So we have SO24, which is equal to 14. Right, that's 12. So we have 2 extras here. So this one's going to be trigonal planar. Trigonal planar means Sp2 hybridization, correct? How about ICL5? We got 6 times 7 is 42. So your chlorines are like that. 2, 4, let's see, 5 times 8 is 40. And 6 times 7 is 42. So we have 2 extra electrons here. So 1, 2, 3, 4, 5, 6. That's octahedral, which means D2sp3. I'm not putting the bond angles in here yet. How about this one? Krypton difluoride. So that's 8 and 14 is 22. That's 8, 16. And that's 4, 6. 1, 2, 3, 4, 5, 6. So we got 1, 2, 3, 4, 5 groups means trigonal bipyramid. Right? So that's DSP2. Okay, now for the bond angles. This should all be 109.5. Or that's our starting point anyway. These are linear. This is only 180 degrees. Sp2 is trigonal planar, so the bond angle should be 120 degrees. Right. This one is D2sp3, which is octahedral. So you've got 180, you've got, and 90. That's it. And trigonal bipyramid. Oh, bond angles. Okay, that's true. That's true. That's true. That's true. But for this one, the bond angle, let's see, where do these, in a trigonal bipyramid, where do these lone pairs go? They go on the triangle in the middle. So the only bond angle here is 180 degrees. If we're going to stick to the strict definition of bond angle, that's it. All right, there's our ammonia. 120, yep, that's right. That's right. 180, nonpolar. Well, it didn't ask us polarity, but it's true. CO2 180, Sp hybridized, yep. And ICL5, 90 degrees. ICL5. Oh. 90 degrees. Okay. Yes. Yes, that's right. Because the lone pair is going to go on the apex. Right? The lone pair go on the apex of this octahedral. So the 180 degree is not an option now because we don't have a chlorine up there. Right? It's only 90 degrees. I stand corrected. All right. All right, this just reiterates low structure, VSEPR, and then use what you know from the electronic structure from VSEPR to determine hybridization. All right, so now we're going to segue into a better theory, one that explains everything much better. Now, we can still use the localized electron model with these modifications. But there's a better theory that expands our capabilities. First, we have to identify the limitations. One limitation of the localized electron model is that it assumes that all the electrons are localized to the atoms. And then the only way that bonds form is if they're shared between atoms. Right? So you look at it sort of through a small tube, and you're only seeing part of the molecule each time. And we have to add resonance very often to accommodate the different Lewis dot structures. Right? And that would expand into our hybridization model also, we'd have to invoke resonance each time. It has difficulty with molecules that have unpaired electrons. I think we had one, I don't know if it's in this class, NO2. All right, that's 5 plus 12 is 17. Like 2, 4, 13. So this takes care of 12. And the only place for the other one is there. Now we can take this one and make a double bond. That's okay. And that gives this one 2, 4, 6, 7. We'll make an octet. But this unpaired electron doesn't fit well into our model. We might want to say that that's trigonal planar. And based on what we've got available to us, that's the best we can do. But it really is not an adequate explanation for that example of a free radical is what it is. An unpaired electron is a free radical. Oops. Unpaired electrons, and it doesn't provide direct information about bond energies. We sort of gave an idea of what the bond energies should be. We didn't actually quantify them. When we said when we hybridize an S and a P orbital, the energy should be somewhere in between. And we just sort of plastered it up there on the board without putting numbers on it. And the theory cannot tell you what the bond energies are. Okay. This is for classes that meet twice a week. So we're going to carry on. So now we're going to introduce a new theory called molecular orbitals. What molecular orbital theory does is it takes all the electrons, the bonding electrons in a molecule, and shares them among every atom. So now they're community property. They don't belong to any one atom. And the orbital structure is based on the whole molecule, not just individual atoms. Okay? So here's a comparison of the two. We rely on atomic orbitals for the localized electron model, whereas we have this new class of orbital called the molecular orbital for that model. The quantum mechanics of individual atoms are sort of pushed out and extended to the molecule, whereas the molecular orbital model uses a whole new calculation for the quantum mechanical calculation based upon the whole molecule. It's a different math. We assume the electrons belong to the atom of their origin. Whereas here, all the electrons are delocalized. That's the magic word. In the molecular orbital model, the electrons are delocalized over the entire molecule. We still have 2 electrons per orbital. That's consistent with the molecular orbital model. And we still have quantized energy for the wave function that solves for the probabilities of the electrons in these orbitals. It's a little different calculation as I understand it, but the molecular orbital wave function solution also quantizes energy. So we haven't abandoned that concept. Okay, so how do we do it? when a molecular orbital model is proposed for a given molecule, the number of molecular orbitals that are constructed are equal in number to the atomic orbitals that were put into the construction. So if you have, let's say, let's use methane then. So how many atomic orbitals are going in? Well, hydrogen is donating 4 1s orbitals. Okay. Carbon is donating 2s orbitals and 2p orbitals. Okay. So we're going back to the original, the source, not the hybridized ones, but the source. So we have a 1, let's see, 3 of these, right? So we have 1, 2, 3, 4, and 4 is 8. So we should have 8 molecular orbitals proposed for this molecule. The numbers of orbitals are conserved. How do we do that? Well, there's a concept we call bonding orbital versus anti-bonding orbital. And it's really not that complicated if you consider the bonding orbital to be the lower energy one and the anti-bonding to be the higher energy. So if we have 8, for instance, if we have 8 molecular orbitals for that molecule, then we should have 4 bonding and 4 anti-bonding. That's how we conserve orbitals. Now, we're going to sort of, it was pretty easy to rationalize a sigma orbital between 2 atoms, right, like this. That's definitely a sigma. There's only one of them. But when we think of sigma orbitals in the molecular model, we can still consider those 2 as on axis, but they're formed differently. In fact, everything goes into the mix, and then you pop out so many sigmas and so many pi's. I need to show you an example to see how that works. Now, once that we've made these molecular orbitals, the atomic orbitals, they no longer exist. You can still keep the molecular orbital theory takes even the core orbitals and incorporates them into the molecular orbital model. But since they're not, we can consider those lame ducks. So usually when you draw a molecular orbital diagram for a molecule, you leave out the core orbitals. Sometimes they put them in, sometimes we leave them out. They're not that important to describing how the molecules are put together. And it can get really complex, so I'm gonna stick with the simpler versions at this stage. Let's see, did I miss something? Yeah, I skipped it. Let's see.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. That wasn't a complete description, but hopefully we'll get there. The reason we can discuss these orbital scenarios in terms of waves is because electrons can be treated as waves. They can be treated as particles, they can be treated as waves. We've already learned that much. So when two waves are occupying the same space at the same time, we say that they are superposed upon each other. And the interference, we just saw that discussion, where you can have two types of interference. When they are superposed on each other, you can either have destructive or constructive interference. We take advantage of that concept every day. Just turn on the radio, turn on the television. We use constructive and destructive interference in what's called multiplexing. Where you can take a single carrier wave, like you tune your AM radio to, I don't know, 620 in my neck of the woods, 620 AM, which is 620 kilocycles or kilohertz. And then upon that wave is superimposed a signal, a voice signal, perhaps, or a music signal, whatever it is. And the wave that goes out as broadcast is a complex mix of constructive and destructive portions of the wave. So when it reaches its destination, we have our receiver tuned so that we'll accept the carrier wave frequency at 620 kilohertz. So all we have to do is match that wave with a 620 kilohertz circle in such a way that it cancels the carrier. 620 kilohertz, and it flattens it out like it did on that, where it showed on that diagram, where there was flat and looked like nothing's happening. That cancels out the carrier, and then what's left over is the signal that you superposed on that carrier. Now, multiplexing, that's not multiplexing. Multiplexing is where you can put multiple signals on the same carrier. In fact, you can stack carriers on top of carriers. And that's how we get lots of information traveling through these little bitty wires or optical fibers by multiplexing. But it's the same principle. You just have to be able on the receiving end to extract the information from that signal. Interference, constructive versus destructive. Okay, we had that described in the video. And this is what I was discussing just a minute ago. They can produce complex patterns of interferences. Okay, so when those waves interact, in terms of our molecular orbital model, if they destructively interfere with one another, when you combine atomic orbitals from, well, in this case, just two hydrogen atoms, when you combine those, you can get two possibilities. The wave can either destructively interfere and produce an antibonding orbital, or it can constructively interfere and produce a bonding molecular orbital. So notice that the bonding molecular orbital, these are probabilities for electron densities. Right? So the antibonding orbital finds a node between the nuclei. Right? So that's one reason we call it antibonding, because it doesn't form a bond. Whereas bonding forms a density that's between the nuclei. And that would represent our sigma bond. Okay. So we're calling molecular orbital 1. Yes, molecular orbital 1 is identified as the bonding orbital. All right. That's the bonding. It's lower in energy than either of the s orbitals that came from the free atoms. Whereas the MO2 or the antibonding orbital is higher in energy than the s orbitals from the atomic source. And this is what a diagram would look like. So here are the individual atoms with their atomic orbitals on either side. And then when we form the bond, we get both a molecular orbital here that's bonding and a molecular orbital here that's antibonding. Okay. This is a symmetrical molecule because both the atoms are equivalent. Right? Those are the easiest ones to deal with. The problem arises when you say bond hydrogen with maybe silicon. And their atomic orbitals are way off kilter. So you need some complicated mathematics to say, all right, where is the energy level of each of these antibonding and bonding orbitals? So that takes a little more doing than we have available to us here. But notice that we have one electron from this hydrogen and one electron from that hydrogen. And now they go into the molecular orbitals. And we do the same thing here. We fill them up like we did for electronic structure of atoms. We fill them up from lowest energy to highest energy. Well, we've got two electrons available. So we put both of them in this molecular orbital. We still obey Hund's rule. We put one in. Okay, that's it for that orbital. So we have to put the other one in there, opposite spin. So that's why they both go in here, and there are none occupying the antibonding orbital. Okay. That's right. The molecular orbital model still produces electron distributions and energies that agree with our basic ideas of bonding. That's true. We just formed a sigma bond between two hydrogen atoms. Let's see. That's no new information. Okay, this just reiterates what I've said before. We conserved the number of orbitals, right? We started off with 2, we ended up with 2 molecular orbitals. And the 2 electrons went into the lowest energy orbital. Okay, Now, we can use that information where the electrons go into the bonding and anti-bonding orbitals. Particularly if we have a bigger molecule and more molecular orbitals available, and they stack up bonding, anti-bonding. Then you might have a bonding, bonding, anti-bonding, anti-bonding, and on up, higher energies. And you start filling them in. So at that point, some of the anti-bonding orbitals will get electrons because they're lower energy than the next bonding above them. When that happens, we can do this calculation called bond order. And the calculation itself gives you a number, and it doesn't have to be a whole number. It can be a fraction. And the larger the number, the stronger the bond. The larger the bond order means greater bond strength. And this, for the whole molecule, is not just for individual bonds. This is for the whole molecule, the bond strength. So this should be, I don't know, maybe in quotes or bonding strength, something like that. Not to imply that this is individual bond strength. This is for the whole molecule. And the bigger the number, the better. So we take the number of electrons that are found in bonding orbitals and subtract the number that are found in anti-bonding orbitals, divided by 2, and that's your bond order. So for instance, the dihydrogen molecule, we noticed that we had a sigma, a 1s sigma, and we had a 1s sigma star. The star is what we use for anti-bonding orbitals. So this shows you the source. It came from 1s orbital, and this is, we always have sigmas first. We never put pi's in there until the sigmas are accounted for. So this is all you have available for that. We put 2 electrons in there. So we have 2 minus 0 divided by 2 equals 1. So the bond order is roughly equivalent to, when you have just diatomics, you can make this assumption, is roughly equivalent to, in this case, a single bond. Bond order 1, single bond. If we had bond order 2, we probably would have some pi molecular orbitals involved. And then you would have a double bond. Okay. Let's see. All right, so here we've calculated bond order for hydrogen and got the same answer as I gave you before. I wrote that wrong. We put the 1s as a subscript. The sigma is more important. So we say, all right, this sigma is derived from 1s orbitals, and this one's derived from 1s orbitals, but it's a star. So it's an anti-bonding orbital. For this example, say we have an H2 minus ion. That means it has 3 electrons, right, to distribute. So we've got the sigma 1s here and the sigma 1s star here, but we've got 3 electrons. So this one's filled up, so we got to put the extra one up here, right, in an anti-bonding orbital. So when we do the bond orbital, bond order 2 minus 1 is 1, divided by 2 is 1/2. So we've decreased the strength of the bond from 1 to 1/2. So this is a less stable molecule. Let's see, we're going to do the other. I thought we were going to do the H2 plus. The H2 plus will give you a similar answer. If you only had 1 electron to go, it'd be 1 minus 0 divided by 2 is 1/2. So H2 neutral is the strongest. H2 minus or H2 plus are both weakened. Oh, we got another video.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have one electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
What we've been looking at so far are homonuclear diatomic molecules. They are the simplest ones to diagram, the easiest to diagram. And you'll notice that the lecturer was only describing valence orbitals. Right? In fact, he went above valence orbitals because he was only interested in the p orbitals. He didn't even talk about the s orbitals. Because by that time, the s orbitals, both the sigma and the sigma star from the s, were completely filled. So if you put those values into the bond order calculation, you come out with exactly the same number that he did. Okay, he mentioned paramagnetism, but he didn't say anything about diamagnetism. Those are like flip sides of the same coin. Paramagnetism is demonstrated by a substance that is attracted into a magnetic field, and oxygen is just that way. You've seen, I don't know if you've seen these before, I've seen them. Big horseshoe magnets. They're monsters. And they might even have an extra metallic thing here. So inside that gap is a massively strong magnetic field. And if you pour liquid oxygen into that field, it will stay there. It won't drain through. what's happening is with those two unpaired electrons, they both have the same spin. They don't cancel their spin out. They reinforce their spins. The rest of them below them, let's see, the next one will be, let's see, here. Would be like this, 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 this. Those are paired. So you can't induce a magnetic reaction in these, but you can in these because they're unpaired. And what happens is they produce a magnetic field in opposition to this one, and the opposing force holds them in place. Okay. If, on the other hand, you set up a magnetic, a molecular orbital model for your molecule where all the electrons are paired, then you won't get that paramagnetic reaction. You get a diamagnetic reaction in which the force is repulsion. So when you pour, say, a liquid, let's see which one, nitrogen, I think works, nitrogen through here, then, yeah, that's right. All the electrons in that model for nitrogen were paired. Pour a liquid nitrogen in there, it goes right on through. No reaction. That's a diamagnetic. Okay, we can measure paramagnetism and diamagnetism using a device. This is kind of a stylized version of it, but it represents reality. In some form or fashion, you have a very, very sensitive valence, and you lower your sample into a strong magnetic field. And you can sense, as you approach this magnetic field, you can sense a pull on that valence if it's paramagnetic and measure the force. Whereas if it's diamagnetic, then it'll descend in that magnetic field. You won't feel anything coming into it, but you might feel something. Actually, you do feel something. You feel a repulsive force. So you measure an attractive force here for paramagnetic and a repulsive force for diamagnetic. Oh, Professor Dave wants to talk to us.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star antibonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma 1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital. But on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called Sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So this is where it took him 10 minutes to get to this point. This is where we talk about sp mixing. And your review document has a diagram in there that's a little bigger than the one that's in the slides. Normally what you would see is when you get to the p orbitals, you have the sigma p orbitals formed first. Then you get the pi's, and then the pi stars, and then the sigma stars above. So the way I look at this to rationalize it, to make it easier to grasp, is that the pi's are in the middle when there's no mixing. And then when there's mixing occurred from nitrogen on over to the left, then the pi's, the pi and sigma switch. Now you have the pi on the bottom and the sigma in the middle, next to the sigma, the pi star that's coming along. So they're stacked like pi sigma with mixing. And then with no mixing, you have sigma pi sigma. And this is not something you have to memorize because, like I said before, if the information is in the review document, it'll be on the exam. So if you need to reference it, it'll be there. This is another way to look at it. Oxygen and fluorine have no sp mixing, whereas boron, carbon, and nitrogen, the diatomics for these molecules, have sp mixing. And you see that the correlation here between paramagnetism and diamagnetism is directly related to the unpaired electrons. So diboron has unpaired electrons, it's paramagnetic. Dicarbon has none, dinitrogen has none, so they're both diamagnetic. We've already seen oxygen is paramagnetic, and fluorine has all paired electrons, so it's diamagnetic. That's one of the things that the molecular orbital theory can can do, can predict these behaviors, whereas the valence bond theory cannot. So this is just to illustrate what I was saying before. These two swap places. And Professor Dave was right. When you're calculating the bond order, this doesn't matter. It only matters when you're considering how the orbitals fill in. The Aufbau principle fills in these orbitals based upon their position. Okay. Oh, I just made a note. Some authors call this sigma pi mixing rather than SP mixing. Okay, so what do we do with heteronuclear diatomic molecules? For instance, here's carbon and oxygen in carbon monoxide. Well, carbon starts off at a higher energy level than oxygen does, right, for its atomic orbitals. So we get a little different arrangement of molecular orbitals. So we're still going to have the sigma here, right, formed from the 2s and the 1s. Oxygen, let's see. No, that should be 2s, right? I made that note here. This should be 2s. So the 2s orbitals form this sigma, and then the sigma star that's formed from them is up here. So the sigma star is higher energy than the original atomics, and the sigma is lesser. Right? That trend hasn't changed. It's just their relative position. I mean, their absolute values have changed. And then here we get the sigma pi, pi sigma. So this is telling us that there's no SP mixing here, right? Because we've got the pi's in the middle, right here and here. Except they're relatively different in energy level than these guys. Instead of having this one down here, just above that one, now this one is high enough energy so it sits in here. And that influences the way that you insert the electrons when you start filling them in. Right, so we've got 2, 4, 6, 8, 10. So we got 2 here, 4, 6, 8, and 10. So this molecule should be diamagnetic. And in fact, it is. What about this one? Heteronuclear Hf. Well, since hydrogen only has a 1s orbital and fluorine has a 1s, 2s, and 2p available, how do they combine? Well, the 1s of hydrogen combines with the 2p of fluorine because the 2p is higher energy and is available for this one. Now, I assume that they've come up with this arrangement mathematically. I mean, there's no logical way to explain why the 2s here didn't overlap with that, except that the 2s is filled already with electrons. So we don't even use the 2s from fluorine to form these these molecular orbitals. So you can see it can get pretty complicated pretty quick. Okay, let's see. Probability distribution should put the electron density closer to fluorine. Even in molecular orbitals, you would see the, let's see, let's back up. Come on. Here. Right. If you see the energy level here is closer to the fluorine energy level when it forms, right? Further away from the hydrogen. I interpret this as a molecular orbital explanation for the difference in electronegativities. You would find this energy level closer to the original energy level of the fluorine, so the electrons would spend more time close to the fluorine. And I would expect to see that trend for any comparison of different electronegativities. Okay. All right, no, that's exactly what I just said. All right, here's another concept. And I think this is the last one of the bunch. Talk about delocalizing in various types of molecules. And yes. So in this case, in this last discussion, we're actually going to combine concepts from the localized electron model and the molecular orbital model. To help us explain what's happening. This is a valuable tool when the molecules under the localized electron model would have to be explained using resonance. Okay, so we have a molecule that is bound together with molecular orbitals, but it seems to be, well, the molecule itself, where we would normally try to represent it as resonating forms, is better explained if we incorporate the delocalizing nature of the molecular orbital models. So let me show you an example. That's the way we would draw a benzene ring. That is, there's a carbon here. In organic chemistry, whenever you have two lines come together, it's always a carbon. We just don't draw them in. But we also know that there are only 6 hydrogens here. And if we draw the Lewis dot structure, the potential is to make our octets. We would have a double bond there, there, and there. So that would give you 2, 4, 6, 8, 2, 4, 6, 8 all the way around. But you can probably see that, well, instead of making the double bond on this side, why don't we put it on the other side? There, there, and there. That's perfectly reasonable. So the localized electron model would say, all right, we got to resonate between those two versions. But if we do that, that means that these double bonds have to be stronger and the bond length has to be shorter. But we know it's not. They're all the same length of bonds. They're all the same strength. So the molecular orbital model, which would be pretty complex for this molecule, would give us a structure that delocalizes the electron over the entire molecule. And one way of visualizing it is also incorporates hybridization. Right? So around each one of these, you got 1, 2, 3, right? So that's Sp2. So if we invoke Sp2 hybridization, then we have unused P's. So the unused P's overlap all the way around, and they form something of a donut of electron density above and below the molecule. So with that being said, we also know that these types of molecules, which are known as, see, I painted myself into a corner. Shoot, hate it when that happens. Maybe I'll remember in a second. So there's our resonance structure for benzene. Aromatic, that's the magic word. These aromatic molecules are extremely stable. And it's because of that delocalized electron density that puts them at lower energy. They're much more stable. So we have our sp2 hybridized orbitals here that give us the sigma bonds and give us the sigmas there. And then the unused p orbitals, let's see, here we go, overlap in a continuous. We would expect, if we were going to do a p orbital overlap, you would only get a double bond here and a double bond there and a double bond there. But that's not what happens. The molecular orbital model says that no, these molecular orbitals would smear over the entire molecule, and that adds extra stability to the molecule. When I was studying soil chemistry, actually it was soil microbiology, we learned that in nature, when a tree falls, or when a plant dies, or some, usually a plant dies, it decays in a sequence. Right? First, you have the physical destruction. You have beetles and worms and fungi and everything. They go in and they break it apart, make smaller pieces. And then the more easily decomposed molecules go first, especially the sugars and carbohydrates. They go really fast. Then you get proteins, and then the fats go, if there are any, the lipids. The last things to go are, well, cellulose for a different reason. Cellulose because most organisms don't have the enzyme system to break it apart. But it'll go. And then what's left is what we call lignin. This is these are long molecules, and they've got these aromatic rings embedded in them. And they are very difficult to break apart. It takes microorganisms that are specially adapted with enzyme systems to do that. So that just illustrates the fact that these molecules are very stable. I don't know why I left this one in here. The nitrate ion is another example of delocalized pi bonding. So instead of getting just one pi bond between two molecules, it's spread out over the whole molecule and stabilizes it. And that's characteristic of many of the polyatomic ions. That's why they behave as single units in a reaction, and they don't break apart easily because they're extra stable. Okay, one last thing. How do we gain some of this information? Well, one of these techniques that we can use is called photoelectron spectroscopy. And this is a way of determining the energies of electrons in individual atoms as well as molecules. And it's a way of confirming what we predict about the energies of molecular orbital electrons. And if we match them up like this diagram does, we find that these high energy photons, which are usually X-rays that we fire at the molecules, eject electrons from the molecules. And remember the photoelectric effect. I don't know if we discussed that in this class, where you have the metal. Yeah, we did. I'm pretty sure we did. And we fire wavelengths of light with certain energy. And if we reach a certain threshold frequency, high enough, then an electron will be ejected. That's the photoelectric effect. Well, there's a minimum amount of energy required. It's called the work function. So much work has to be done to eject the electron. Then any extra energy is converted into kinetic energy. Right? So if we know the kinetic energy, we know the energy of the light coming in. We can measure the kinetic energy of the electrons coming out because they produce a current at a given voltage. and we can measure the kinetic energy. And by that, we can determine what was the energy of the electron before it left the surface, before it left the molecule. Okay, so when we do that calculation, we find that we have the spread of electrons at these different energy levels. And they correspond, these jumps correspond to electrons that were at this level, at this level, at this level, and this level, exactly as predicted by the molecular orbital theory. Right? The mathematical gyrations that you go through predict energy levels. It's more, in fact, it's too complex to do by hand. You need a computer to do it for you. But this is just, the only reason this slide is here is just to say that this method confirms the molecular orbital theory energy levels for the molecules that are being described. Okay, that's it.